in this session, which is actually number 14, we're going to talk about physical and chemical change. This is where we do things to stuff, okay? And we're going to add stuff to different stuff and get new stuff, right? There's a few words that we've got to come up with first before we start adding these bits and pieces together. So let me just take this one here. Just take the power cord off there. First of all, let's just have a look at. Firstly, let me just put down this word. Endothermic and exothermic. Thermic comes from the word thermal, which means heat. You know, gliders ride the thermals. It's hot air currents going up. Gliders ride it. Birds of prey use it to get heights so that they can see vast areas for their hunting turf, for their terrain. That's a thermal. It means that. So this has got to do with heat, right? This has got to do with heat, right? And this has also got to do with heat. Okay. Now, what do we mean? Endo and exo. Okay. That's obviously two different types. Well, let's just break it down. Okay. Exo, exit, out. Okay. Let's say X. Look what Kevin wrote. XT. Exit. Okay, let's do that. Exit, out. It's the way out, isn't it? The exit sign means the way out. In other words, this here is heat. Heat leaves. Okay? This here is the opposite of heat goes in. Okay? So heat goes into the reaction, and heat leaves the reaction. So it's out of reaction, into reaction. Exo, exit, go out. Endo, come in. It's just the opposite. So remember, exo, exit, heat goes out. Okay, that's the first one. Another word that we've got to look at here is we're going to look at we've got that one there. We've got here reactant and products. Well, this is we add some stuff plus more different stuff, and we get new stuff. In other words, products is this here. We take bits and pieces and we get products. We get something different. Okay? If you put an acid, like we've said before, on marble, you get different stuff. The marble dissolves. Okay? And we get new stuff. Reactant is the stuff that reacts with each other. It takes part and it forms products. It forms new stuff. Okay. Another word that we've got to know. There's two of them here. Synthesis and decomposition. Okay. This is make stuff, and this is break stuff down. Okay? It decomposes. What happens when leaves decompose? They turn into, you put them in a hole with a bit of lime on it, that's slaked lime, and what happens is it eventually turns into compost, doesn't it? Fertilizer. Because it breaks down, it decomposes. Decompose it, breaks down into its different parts. Synthesis is we make stuff. Okay, you've heard of it's a synthetic diamond. It's a fabricated, it's made. Synthetic, okay, it's produced. All right, so we make stuff and we break stuff down. So if we just remember back, just for quickly remember, we made water out of hydrogen gas. Now remember, we've got to start using these so that we know what it is. Because if I tell you calcium, you don't know if it's the powdered solid calcium or if it's dissolved in water or if it's linked to something else, do you? We got no clue what it is. So we have to use these little descriptors at the back now. Plus oxygen gas, okay, remember, went to water. And that was a different phase. It was liquid, right? And we had to balance it. I'll get to the rules for balancing. Oxygens, we've had 2 and 4, so we need a 2 there. Remember, it means we need 2 to 1 to get 2. This is beginning to get towards the recipes for making stuff. Okay, so that was synthesis. We made water out of the 2 basic elements, didn't we? But what was electrolysis? Electrolysis was the breaking down. We took the 2H2O liquid, we added a little bit of acid to make it into a electrolyte. The electrolyte carries current, right? And it broke down and we ended up getting what? Hydrogen gas, and we got O2 gas bubbling off. Remember that? So that's the electrolysis process. That's the decomposition here. Decomposition. It's decomposition. It's breaking it down, okay, from the stuff it's made of, and we take it apart into its basic constituents. Okay, that is a decomposition reaction. Another one is mercuric oxide, HgO, right? If you heat it, okay, now you say delta. That usually in chemistry means heat. Okay, usually means add heat to it. So if you add heat, we get mercury, liquid, okay, because it's a metal, it's liquid, okay. It's fantastic stuff. I don't know if you've ever seen it. Please don't play with it because mercury actually is highly toxic. A long, long time ago, people used to hold it on the palm of their hand and the little bubbles would run around and so forth, and it was too cool for words, you know. I would suppose some people even tried to taste it, but it's highly poisonous. It gets into the skin and it gives mercury poisoning. Hg liquid, and what was given off was the oxygen, but oxygen is diatomic, so it's always a 2 when it's in an element form. When it's in a molecular form, it can be an O2 or it can be just an O. It can even be an O3 or an O4. Remember, sulfate, -2. There's 4 oxygens linked to that sulfur over there, right? So now what happens? That is a decomposition reaction. We're taking this and we're heating it and we are changing it, right? Now, let's have a look at some of the things that do physical change, okay? Physical change. The physical change, right? First of all, basically we've got temperature. Secondly, expansion, contraction. Let me just put contraction, color changes. Then we can have conductivity change. And then we've also got change of phase. Okay, let's just talk through what do we mean by this. Okay, well, a physical change is, well, we've got something over here, and now if we do something to it, okay, add stuff to it, or increase or decrease temperature, right? The temperature can change either if it's an endo or an exothermic reaction, or if we apply to it. Expansion and contraction. If you apply, let's say a piece of metal is in the sun, it gets hot, it expands, it gets larger. We know that with gases. As they get hotter, they expand. That is why a cylinder of furniture polish that we use, any of these sprays, deodorant sprays, any of those kind of things, it's got a big warning. Do not throw into a fire. Do not incinerate. Why not? It's full of gas. It's pressurized. So as that temperature goes in, those molecules of gas start moving faster, right? Why? Because remember, we said temperature is a measure of kinetic energy, which is a half mv squared, right? A half. Now the mass of the molecule, atom stays the same, molecule, atom, okay? But what changes is the velocity. So as the temperature goes up, these things start going faster and faster. As they go faster and faster, more of them are hitting on the side of the container, which means the pressure builds up. The pressure cooker, remember, inside there when you lift the lid, it all comes out. That is the increase in pressure, and it will blow up. It will explode, okay? A lot of people have been injured by this process. Secondly, there's a conductivity change. As we heat up the copper wire, what happens? That once again, the velocity starts, I forgot I had it on the eraser, the velocity increases. So as we're heating it up, what's happening? The electrons, everybody's moving around frantically faster. That makes it more difficult for the electrons to move through the wire. So the conductivity changes. As you cool it down, right, it gets cold. The molecules all cuddle up together, or the atoms and the electrons all cuddle up together, and they're not moving around, so the electrons can flow easily. They're not bouncing off each other. Remember, this guy's trying to get from this side of the wire to that side of the wire. And what happens? He's being bounced around. He can't get through, right? There's too much energy. The colder it gets, the easier it is. That's what a superconductor is. It's cold. It's made very cold, chilled right down. So the atoms, the molecules are hardly moving, the electrons. So the current can just keep flowing in there with very little resistance to the current flowing, okay? Color changes. We've all seen the color changes. It's a physical change. It changed from blue to red, yellow, green, whatever the case might be, all right? Change of phase. Well, obviously, it can change in phase. It can go from a solid to a liquid to a gas, i.e. ice. It is still water, but its physical properties have been altered. It was a solid, now it's a liquid, and you keep heating, it changes to a gas, okay? The other one, remember, it can go from a solid to a gas straight away. That is called sublimation, when it changes from one to the other quite quickly. Dry ice, carbon dioxide, or iodine also does that, okay? So those are chemical changes, right? And we've spoken about those, okay? And the endo and the exothermic. Now, let's have a look at a chemical reaction, right? I am going to choose, and I'm going to use ammonia. We are going to synthesize ammonia, which means manufacture. Why? Well, because we want to make household cleaners, don't we? So we're going to manufacture ammonia. Right. Now, how do we go about this process? Well, first of all, what's it made of? It's made of N and H, nitrogen and hydrogen. Hello? Nitrogen and hydrogens, right? It's made of these guys. Now, what happens here is we've got nitrogen is a gas, isn't it? And hydrogen is a gas. And we want to make ammonia, NH3. This is on this side over here. Let's put them in, shall we? These are our reactants. This is what we're going to use to make it. They're going to react, and they're going to manufacture a product. Remember? Add stuff and make new stuff. We're going to make ammonia. So and here we go, okay? there we go. There's one molecule of N2 and a molecule of H2. Now, when we manufacture this, okay, we know we've got to balance it, but what's actually happening at a molecule level and at an atomic level? Well, let's say, here we go. I'm going to put in here, can you see there's my one molecule of N2. Each one is an N and an N, right? And I put in here, let's change the color just to keep them separate. Let's make it a blue and a blue. Can you see there's an H and an H? Okay, but now, right, we are going to form NH3. What does NH3 look like? It's H, H, H with an N, which was green. Right? That's what it looked like, wasn't it? Blue. I'm just trying to keep the colors here so that we've N, H, H. And if we really want to remember, it looked like this, didn't it? N, H. That was the Cooper diagram. Remember the Lewis diagram? Had a 3, nitrogen's -3 valency. It had 5 valence electrons, valency electrons, therefore it had a lone pair on top. Okay, remember up here, this lone pair, over there, okay? They don't bond, right? So we've got that. Now, that's what physically happens. So there it is, isn't it? That's what's happened, right? There she is, okay? I need my other green one. Sorry, I don't have the same, but there we go. We formed N and 3 H's, okay? That's what it looks like. Forget the actual shapes of it for the moment. Okay, now that's fine. But let's see what we started with. We started with these two, didn't we? We said, right, we break you up and we break you up, okay, so that you are free. Then along comes this one nitrogen, okay. Let's just break them up now. Green, there's a nitrogen, and there's our other nitrogen, okay. There's our broken up molecule down to atomic level. And let's break up our blue. But can you see here's a problem now? We haven't got enough H, have we? We haven't got enough hydrogen. So we need more. So we're going to have to add in another H. Another H is another H2, isn't it? Like that. Can you see? Now that's going to split up and give us an H and an H, right? Can you see that's what's happened? Now, have a look here. Now we say, okay, we are able to link these three, and what's that going to do? It's going to make one of those. So there we've got one NH3. But we've still got a lone N out there, okay? We've got this guy and one H, so he now requires partners as well. He says, but hold on, you can't leave me here alone, right? You've got to finish this. I need to be used up. So you've got to add another H and an H there, right? And what does that allow? Well, it allows us to do that. So that forms another of NH3, doesn't it? Okay, green N, there it is, and my blue ones. Where are you, blue guys? There you go. NH3, right? So here you can see what actually happens. When we add these chemicals together, we have to make sure that we balance out, right? We've got to conserve. There's the 3 laws: the conservation of atoms, the conservation of mass, and law of constant composition. What are we talking about when we say the conservation of atoms? Well, simple. Look, what you put in, you must get out, because all you've put in is that. If you are making a fruit cake, You put all the stuff, the eggs, the sugar, the milk, the flour, the fruit, whatever, all together. You mix it all up, butter and goodness knows, put it in a tin, right? What you put in there is what you're going to get out, isn't it? Because you're going to take the cake and cook it. What's going to happen? What are you going to do? You will smell the cake cooking. Essentially, that's water vapor coming off, okay? So if you trap that as well and you add all the masses together, the molecules you put in must be equal to the molecules or the atoms you put in must equal the atoms you get out. So therefore, if I'm going to make this, and I'm saying we are making it, therefore we have to put in 1 atom of that. Let me change this. 1 atom of this and 3 atoms of that, and we get out 2 of that one. Now, if you do in the workbooks, there's quite a lot of emphasis on this. Play with them. You'll see that when you break them down, look what I did. I broke it down and then I said, how many do I need to complete that? Okay? It's actually not a complicated process, but it is critical in order to understand this section, because this now builds on hugely for the next year and for grade 12, and if you're going further with chemistry. So let's have a look here. We say, okay, that is what has happened on that. So it's a synthesis reaction of ammonia. We have made ammonia and synthesized it, right? So let's take, for example, conservation of atoms. What we said is all the atoms that we put in must be used, not used up really, but if this is going to be, let's say, our make, okay, produces line, okay, there to there. So the atoms here, total number of atoms there must be equal to, yeah, you're right, total number of atoms over here, okay, of the same stuff, right? So if we put in calcium and hydroxide over there, all right, we have to have the same number on the other side. There's nothing else being added. We can't suddenly come up with nitrogen and boron, okay? It wasn't there in the beginning. So the reactant govern what we're going to get out, okay, doesn't it? So we've got to use all of the atoms of the reactant, and they've got to be represented on both sides. It's a mathematical equation. The left-hand side must equal the right-hand side, okay? Number of atoms on the left must equal number of atoms on the right. It's a fundamental prerequisite of this, okay? The second is the conservation of mass. What does that mean? Well, like I said, if you take all the ingredients for a fruitcake, okay, like so, plus some of this, plus a bowl of that, and I don't know, whatever, a pile of fruit, okay, and you add all that together, all right, you mix it and you put it into a, let me try and draw it a little better. We put it into a tin, okay, and we add heat, all right. What happens? That is in the tin, isn't it? Now, hold on. Okay. You've added, let's say, a total over there of 2.5 kilograms. It's a big cake. So everything adds up to 2.5 kilograms. On this side, you've got the baked cake, hot cake, because you've added heat to cook it, right? Plus, what gets given off is, I'm going to say vapor, gases, okay? Mainly, let's say water, and it carries some aromatics with it, okay? But water, right? The total of all of that must be 2.5 kilograms. Because why? Mass cannot be created nor destroyed, merely changed from one form to another. The law of conservation of mass. Law of conservation of mass. You can't create it. You put in 2.5 Ks, the total must be 2.5 Ks. Obviously the cake is not going to weigh 2.5. The cake might weigh 2 kilograms, and maybe if you catch the water, you've got 0.5 kilogram of water that has come off there. All right? That's what we're talking about when we talk about this process, conservation of atoms, conservation of mass. And the law of constant composition is this. Okay? If I am going to make water, okay? All right? We are going to manufacture, synthesize water. So H2, gas, remember, plus O2, gas, goes to H2O, balance it 2 and 2. All right? What does it mean? It means that there is always going to be a ratio of 2 hydrogens for every 1 oxygen over there. Why? Because if it's not, it is not water. It's H3O or something else. Or, for example, H2O2. Right? That exists, most definitely. That is that very pungent smell. When you go into the hairdressers, sometimes even today you smell it still. For those of you who do the surfer look, or especially for the girls, that's hydrogen peroxide. What does it do? Creates a blonde streak. So that is hydrogen peroxide. Okay? And it's pretty stinky stuff. It's a very smelly stuff. So yes, we make it with hydrogen and oxygen, but if it doesn't go H2, 2 H's to 1, it is not water. That's what they mean by the law of constant composition. It must be the same ratios, okay, to create water. The same goes for, I'm almost done, the same goes for nitrogen, N2, okay, gas, plus H2 gas, going to NH3 gas. Okay, let's balance. Nitrogens, we need a 2. Okay, in the next section I'll go through the recipe for balancing equations. Again, well, not again, I haven't done it with you. 2 N's, and I've got 6, so I need a 3 there. This is always going to combine in the same ratio. 1 of these, 3 of those to get 2 of those, and this stuff here, that ammonia, okay, is always going to be 1N and 3H. If it is not NH3, if it's not combined in that ratio, if the ratio is 4, then it is NH4. It is ammonia, right? Ammonium, isn't it? Ammonia and ammonium. Ammonium is the NH4 plus ion, okay? So it's different. It's not ammonia. So that it must be, if it's going to be calcium chloride, it is CaCl2. 2 chlorines to 1 calcium, or magnesium. If it is lithium fluoride, it's 1 Li to an F. It's 1 to 1. Okay? That has to be, otherwise it is not lithium fluoride, it is something else. Okay? Right. Thanks for watching that one. The next one we're going to do is we're going to look at some equations, okay? I'm going to look at acids, I'm going to look at typical reactions there. I'm going to come back and give the recipe for balancing equations, and then we'll move forward. Eventually, the last section is we're going to be doing stoichiometry, which is the one where we do actually the calculations involving how many grams of this must we add to how many grams of that to achieve the reactant, or sorry, the products that we want. Thanks for watching. I'll see you in the next session.